Welcome to a video on the op-amp integrator. We are going to look at the integrator circuit, applications, derivations, a practical implementation, and I'm going to do some simulations afterwards to show you some of the features that we talk about. Okay, so the Miller integrator, it's more commonly known as Miller integrator because you have a capacitor in the feedback path, can be used for area calculation or averaging. Okay, so since integration determines the area underneath a graph, we can use it in that fashion. Okay, the integrator can also be used to convert square waves to triangle waves, since you integrate over time, and we can also convert sine waves to cosine waves, just like we did with a differentiator. Okay, we can also use the integrator to cancel DC offsets, like we did in the instrumentation amplifier in one of the first videos in this series. And one of the most typical applications for the Miller integrator is the dual slope ADC or the integrating ADC, where the input gets integrated and then the reference voltage gets integrated, and they use the time for the integration to determine what the voltage was inputted into this ADC. Okay, so on to the derivation. We can assume that we have an ideal op-amp, and again, the current flowing through the capacitor is the change in voltage over the change in time. And we can find our two equations and combine them to find that we have integration of the input signal. In this case, we have 1 over the time constant, and since it's inverting amplifier, the output is inverted. So 1 over the time constant is our gain in inverted commas for this integrator. Now this time constant, or this 0, we want to place as close to 0 frequency on the Bode plot as possible, so that we have a 20 decibel per decade decline across the board. Right, so this is typically a very, very small number, but the smaller we go, the higher the gain will be. Okay, so you need to strike a balance between the two. Just like the differentiator, our 0 dB frequency will be at this time constant, point where we cross 0 decibels. Okay, then we can also do integration by parts. If you have to do this integration manually, you can integrate every part of a signal and then sum all the values that you got over time to find the actual output. Okay, so let's look at the Bode plot. Our 0 dB crossing. Okay, and you can see the minus 20 decibels per decade right across here up until about 10 kilohertz. You also want to keep the phase constant for the integrator, just like the differentiator. But there is some issues with this, and you need to add a bit of a resistance in parallel to the capacitor, and that will add some phase here at the lower frequencies. So if the phase doesn't bother you, it doesn't matter, but if the phase does bother you, then the integration area will only be between these 2 points where it's kind of a perfect integrator. Okay, so then you need to design for your frequency to be between these 2 points. Okay, now the issue with the ideal integrator is that you have a huge DC offset at the output. So you add a resistor in parallel with a capacitor. And if you add a resistance, there is a discharge path for that capacitor. So typically this resistor is very, very large. Okay, so the time that it takes to discharge is, we call this time constant 2, is C1R2. Okay, and the complete discharge takes 5 times that of the time constant. So 5 times tau is the time that it will take this capacitor to completely discharge. Okay, we also need to add this resistor here to compensate for the offset currents, and resistor 3 is the size of R1 and R2 in parallel with one another. Okay, so if we need to do a design, let's say we need to design for a time constant of 0.15 seconds or a 0 dB of 10.6 hertz. We can just go ahead and choose a capacitor and a resistor. So we chose 10K and 1.5 microfarads. The capacitor will always be extremely large in this circuit. Okay. And let's say we want to have a complete discharge time of 75 seconds. So for this cap to discharge when there's no input on R1, it should take 75 seconds. So 75 divided by 5 will give us our tau 2, and this will give us a resistance of 10 mega ohms. And then the resistor 3 is 10 meg in parallel with 10K, which is roughly 10 kilo ohms. Okay, now I have a signal on this next page that we need to integrate. And then after that, we need to simulate the problem to see if it actually works. So we have a signal with some ups and downs of square waves. So let's break it up into areas. If you integrate areas or places where there's no input, nothing will happen to the output. Okay, so the output will remain constant in any of these areas. Okay, so the best way is to calculate the area of each of these zones, right? And then multiply it with the constant that we have, minus 67 per second, which is just the inverse of this tau and the inversion of our amplifier. That will give us our output voltage. Okay, so the area here is 0.02 seconds and 5 volts. That will give us an area of 0.1. Okay. Down here we have the same, but it's negative, so the area here will be minus 0.1. Okay. And I note down the time where this integration happens. Okay, this will become important for the next table here. Okay, again, another area. And lastly, another area. All of these are negative. Okay, then we take our areas and we multiply it with our constant. So we get an area of minus 6.7 volts, 6.7 volts, 2.68 volts, and 3.35 volts. Right. This table over here is a combination of, we take all of these times where things happens and we list them. Okay. The times indicated in red is where the output is in terms of voltage in this last column. Okay, so between the time 0 to 0.02, no area is added. Okay, nothing happens. Then from 0.02 to 0.04, minus 6.7 volts is added. Okay, so from 0.02 to 0.04, our output should go from 0 to minus 6.7 volts. Okay, so we can put in the area gained in every area, and then we do a summation. Okay, so this output voltage here, in the next area nothing happens. Okay, so 0 minus 6.7 equals minus 6.7. So from 0.04 seconds to 0.08 seconds, this voltage will remain constant as we would expect for the integration. Okay, so basically our output would remain 0 for this first part, and then it should decline to minus 6.7 here at 0.04. Okay, so our endpoint is minus 6.7. Okay, so it's about a bit out of a chart, so down here somewhere. So from here, our signal should go downwards to here somewhere. Okay, and then it would remain constant from 0.04 to 0.08. Okay, so up until this point it would remain constant, and then we have a positive area of 6.7. So 6.7 minus 6.7 would result in a 0. Okay, so this signal should go down to 0 from 0.08 to 0.1 seconds. Okay, so in this time frame it should go back down to 0. So we have area increasing, so this graph becomes larger. Here happens nothing, so nothing happens. And here we have this graph decreasing, so subtracting a bit of what we accumulated on this side, and it goes down. So we would see something similar happening in these next areas. So it's that what I'm about to draw is not accurate, but we would see something like this signal going up, staying constant, and then there would be a huge sudden increase, and then it would remain constant again. Okay, so you determine the areas and then you do the summations like here, and our final voltage should be at about 6 volts. Okay, so our final should look like this. So let's hop into some simulations. So we're going to have a look at this integration problem where I created the signal, some DC offset cancelling, and some Bode plots. So the first thing that I want to show you in simulation is basically I have a sinusoid set up here with a 1 volt peak and a 1 volt offset, and it's how to use integrator to cancel any DC voltage. So I placed the resistor here to discharge this cap, and I put in a huge capacitor to capture any of the DC voltage. So no mathematics really went into this. You can do, but it's not needed if you want to just find the DC value. And I basically made the gain of this 1. Okay, so our original signal, here we have our sinusoid offset by 1 volt. And if we click on the output here, there is a minus 1 volt lying down here. Okay, so if we double click, we have a very small amplitude sitting around minus 1 volts. So you can capture the DC from a signal like this sinusoid and then get rid of it in some configuration. So this is basically how you do DC cancelling. And in the instrumentation amplifier, I used something similar, but I did not have this resistor here. So there's no load on this cap or discharge path or place for this capacitor. The output will not work. Okay, you can see that there is this amplifier goes to saturation. Okay, in the instrumentation amplifier, there is a resistor here where it couples into, and that counts as the discharge path for the capacitor. Okay, so that is how we do DC cancelling. Let's hop over to a next simulation. In the next simulation here, I have an integrator set up, and I want to show you this resistor up here and the discharging of this capacitor. So I have our integration running and it works perfectly. But for this resistor, I picked a 100k, a 1 meg, and a 10 meg resistor. Okay, so a 100k in parallel with a 10 microfarad should have a discharge time of about 5 seconds. Okay, and I have my simulation set up for 5 seconds. So after 5 seconds, the one line should be discharging. The discharge should be less for the 1 meg and much less for the 5 meg. Okay, so this is going to go up to 5 seconds, 50 seconds, 500 seconds. Okay, so let's run this and see what happens. Okay, so our input is this integration happening and then nothing for a very long time. So the last output value should be kept in here. Okay, so let's check. For the 1 meg, we have medium discharging. For the 100 kilo, you can see that it is completely discharged at 5 seconds. And for the 10 meg, look at how long this line is going on here. Here is the simulation ramped up to 50 seconds. And there's the 1 meg discharged, and the 10 meg is still going kind of strong. And here at 500 seconds, the 10 meg is discharged. Okay, so here you can see all 3 of them. So this resistor should be very large if you want to keep a value for a long time. If you're not keeping it for a very long time, you can use smaller resistors, and that is typically how you do averaging. So from the DC problem where we did the extraction, you want that value to be a bit more dynamic. So the 2.2 kilo ohm that was used for integration to just get the DC out is a perfect fit. So the moment that the DC falls away, the output signal will also go to 0. So let's have a look at the AC response of this changing resistor. Okay, so you will see that the phase is flat here at the bottom, and as we increase or decrease the resistor, our phase will become a bit more not flat. So the larger the resistor, the closer this becomes to a perfect integrator. So it is moving this way typically. So the one down here is a 10 meg, which is the closest to open circuit that we can have. And if we remove a phase, you'll see that all of these lines in terms of integration is still falling on top of one another. So nothing happens to the magnitude plot. Most of the changes from this is happening in the phase. So let's hop over to our problem simulation. So in this simulation, I have our integrator that we designed set up without the 10 meg and with the 10 meg. So let's have a look at the Bode plot before we go to the time domain. So putting the two Bode plots on one another, you can see that the phases is a bit different, but looking on this side, the phase is almost, there is what, a 3-degree difference between them. So not much of a phase change. Right, so these two are very close to one another in terms of the phase and magnitude Bode plot. Okay, the difference, however, is going to be seen in the transient. So let's run our time simulation like this. Okay, so there is our input signal that we used in the problem. So we take the output on our perfect integrator without this resistor. There is a DC offset added to this signal. Right. And if we go to the one with a cap, the DC has been removed. Okay, and this flat bits you can see is almost perfectly flat because we used a very large resistor here. Okay, and that is how the integrator works. Thank you for watching, and I'll see you in another video.